¿Vale? Pepa, tú me avisas, por favor.
Pues ya lo que voy a hacer es presentar a Enrique.
Un segundito. Venga, pues...
¿Viene alguien más? Sí, yo Good morning, everybody. Today is, for me, it's a really great pleasure to introduce Enrique Perez-Montero because he produced me to work with one or some studying his papers. That happened when he finished his PhD in Madrid. He was working with Ángeles Díaz and made an extraordinary work, let me say, on abundances, how to calculate abundances in galaxies. She finished the PhD in 2003, and then he has been working in Toulouse, and from 2008 he came to the IEA, working with a as a postdoc with a high doc in the extragalactic group, and from 2011 he became part of the staff. I think that is really, we are very lucky to have a person like Enrique. For many point of view, I think he is the kind of person that I normally name sabios, with the extraordinary work he has produced along these years, and also from the human point of view, I think that we appreciate very much recently the work he's doing in outreach, popularizing science and astronomy for people who have visual problem, as he has, so that it's really an extraordinary effort, in addition to the big work he's doing, an extraordinary effort to popularize this to the general community, and helping other people through the organization of the to become interested in astronomy and science, because astronomy is the science of the light, and so he put, without light, astronomy into the blind eyes, so that this is really great effort and wonderful. Congratulations, Enrique, for that effort. It's very good. So now I will leave you with Enrique, that today he will talk about, of course, abundances in galaxies, but in the Khalifa, that most of the people in the extragalactic department, we have been working in the Khalifa project, so we are very interested in the produce about. He has produced he produced a new paper that has been already published on this topic, and I recommend all of you interested in abundances in galaxies to read carefully this work. It's great. Thank you.
Okay. Thank you so much, Pepa, for this embarrassing for me introduction. Many thanks, and thanks to all of you for being here today. It's for me as well a pleasure to be here today, because the work I'm going to present you today has been a bit challenging in many aspects. First of all, because it belongs to a large collaboration with all the challenges and difficulties that this has, but as well because the last 2 years has been a period in which I have lost most of my sight, so I have to adapt myself to keep myself at the top of research. I think I finally get this point with this paper, so for me it's really a pleasure to present this work today. As you know, I'm visually impaired, I'm almost blind at the moment, but my plan is to keep going in the research and demonstrate the other researchers, the students, everyone, that even a visually impaired person can manage to still doing science. So if this kind of works demonstrate this point, this will be satisfying a lot for me. Okay, the paper I'm going to present has been already published, and it's related with, as Pepa said before, determination of chemical abundances in the Khalifa project. Okay. You will hear every time the name of the slide. This is for me, in order to know what I'm showing to you in the screen every time, because at the moment I'm not able to see what is in the screen. If there is something inappropriate, you tell me, okay? Okay, this is the list of co-authors of this paper. Many of them are here today. Many of them are people belonging to the IAA, because Khalifa is a project which has been led partially here in the IAA from the Observatory of Colorado. I would like to stress the name of Ruben and Pepe Wilchet, the two guys that have helped me more to do this work. But the list of co-authors is long, as corresponds to a big collaboration, as it is Khalifa.
Starbursts.
Just a couple of words about what is the determination of chemical abundances in starbursts. You know that chemical abundances are very important because they give us information about what's the evolutionary status of the object that we study. Metallicity, the metals are produced in the interiors of the stars. So if we know the amount of metals that we can measure in an object, we are able to know what has been the evolution of this object in the past. Okay? When we study the ionized gas ionized by massive star formation processes, what we look at is the emission lines produced by the gas once the very energetic ultraviolet photons have been absorbed by the atoms and re-emitted in the optical part of the spectrum. This is a very great advantage that although metals are not the most abundant elements, chemical abundant elements in the gas, their lines are prominent and are many times the brightest in the optical spectrum. This is why the energetic difference between the levels around the atom are of the same order of temperature of the plasma. So this is why many times the most prominent emission lines are those from oxygen, although oxygen is around less than 1% of the species that we can find in a gas. And another great advantage is that the methodology that we use is appropriate for many different scales, from H2 regions in our own galaxy up to very high redshift starbursts at very short cosmological epochs. So this is important, and the methodology to get information about the metallicity in these H2 regions is very important.
Nitrogen.
Well, one of the implementation I have done for this work is the study of nitrogen. Normally we study oxygen because oxygen gives us information about all the metallicity, other metal species that we can find. But nitrogen is very important. One of the reasons is one of the main coolants, although it is not the most abundant one. But one of the main reasons is that because the instrumental setup of many of the observations in the optical, the N2 line is quite close to H alpha. We look at starbursts, and for H2 regions, for instance, looking at H alpha. And when people ask us about what more information we can get from these H2 regions once we have detected them using H alpha, you look at the emission line right close to H alpha, which is N2, and we use this line to get the total metallicity of the nebula. The problem is that you are the abundance you are going to get is more related with nitrogen than for oxygen. So it is important to know what difference is between nitrogen and oxygen in the set of metallicities that we can get in the H2 region.
N versus S.
The main difference between nitrogen and oxygen is the type of star that produces them. Oxygen is mainly produced by massive stars. It's a primary element, but nitrogen is mostly produced in the CNO cycle of low and intermediate stars as a catalyzer of this reaction, nuclear reaction. This implies that this is mostly a secondary project. That means that the nitrogen to oxygen ratio grows when metallicity grows. There are a linear relation between nitrogen to oxygen ratio and metallicity. Normally, there are several relations that people use, and they say Okay, I assume what's the relation between nitrogen to oxygen, and in this manner, I obtain oxygen abundances using nitrogen emission lines. But the problem, as we can see in that plot, is that the dispersion is very large. It is not so an easy relation between these two elements in H2 regions.
The dispersion.
What's the reason of this dispersion in this diagram? There is a very nice paper by Perez-Montero in 2006. She has, with Pepe as well and Ángeles Díaz, and they demonstrate how the different star formation history in a galaxy leads to very different values of nitrogen to oxygen ratio. Why? Because if oxygen is produced by massive stars and nitrogen is produced by low and intermediate mass stars, the delay in the ejection time before these two elements are ejected into the interstellar medium is quite different. So if the star formation history is different, the relation is going to be different. Another point is, for instance, a really other nice paper by Mike Edmonds in 1990, and he demonstrates that when we are not considering a closed box model for a galaxy, this means that this galaxy, it is not evolving by alone, but either that there is pristine gas falling into the galaxy, or the gas is ejecting enriched gas. This affects differentially to nitrogen to oxygen ratio and to metallicity. I mean, for instance, if a great amount of pristine gas is falling into a galaxy, this implies the metallicity drops. And for instance, the star formation rate is boosted because with the new gas, we are producing new generation of stars. But nitrogen to oxygen ratio remains constant. So there are many different things that make nitrogen to oxygen ratio to be different than metallicity. And this is why it is important to study them differentially.
O3N2.
What happens? Happens that most of the empirical calibrators based on the fluxes of the strong emission lines that we use to get oxygen abundance are based on N2 emission lines. This is one example, O3N2 parameter. It is not valid for metal poor objects, but for metal-rich objects, such as, for instance, the H2 regions in the disks of Caliphate galaxies. It has been widely used, but it depends on N2. And as I show in this plot, there is a great dependence on N over O. If we don't know N over O, we are taking the risk that probably our metallicities are contaminated by the assumption that we are making about what's the relation between oxygen and nitrogen. Okay?
Gradients.
Brief couple of words about what's the importance of studying gradients in spiral galaxies. Well, it is known since 40 years ago or so that most of the spiral galaxies present gradient of metallicity. Most of the galaxies have larger metallicities, larger metal contents in the center of galaxies than in the outer skirts. There is a gradient. And this is related with the fact that galaxies have built their stars from inside to outside. This has important implications when we want to relate the integrated metallicity of a galaxy with other integrated properties, such as, for instance, the stellar mass. Now there are plenty of papers that are trying to relate the stellar mass of a galaxy with metallicity. But what is the metallicity of a galaxy? If metallicity is varying across the radius of the galaxy, which is the value of metallicity? And many times, for instance, in the slow and digital sky survey, when we just put an aperture in the galaxy and we derive the metallicity of a galaxy, the metallicity of a galaxy, my God, when the metallicity is varying a lot for the inner to outside the galaxy. So when we have a spatial resolution to get the distribution of metals across the galaxy, we can get a value of metallicity that is more truthful than just an integrated point.
Gradients in Khalifa.
A very nice paper about gradients in Khalifa galaxy has been published by Sebastián Sánchez. This is a great paper, but it has a problem. It has been calculated with O3 and 2. So we have to think about to what extent not to have taken into account nitrogen has affected the results. One of the results, for instance, in this histograms, the important one is in the middle panel. This is the distribution of the slopes of the gradients, once normalized by the effective radius. And the conclusion is that we have a Gaussian distribution around a mean value, so we can conclude that, in average, we have a universal gradient of metallicity. But what kind of gradient is that? It's a gradient of nitrogen, of oxygen. The problem is that it has been calculated with O3 and 2. Okay.
Khalifa.
So we have calculated again the gradients. In this case, we have taken a large sample of galaxies in relation with that paper of Sebastian. I'm sure that hundreds, maybe thousands of hours have been devoted in this room to describe Khalifa. But in summary, what you know, this is a survey, a great survey made with a 3.5 telescope in Alto with the instrument PIMAS, which is an integral field unit. And this allows us to have access, with a resolution more or less of 1 second, of a spectra of galaxies. Well, in this case, the galaxies were selected in order to cover 1 arc minute or so. So there is a sample of, I don't know the exact number now, but it's between 500 and 1,000 probably. This is publicly available for the community, and it has been released a lot of beautiful papers. Okay, for this work in particular, whoops.
H2 regions.
Okay. I have taken the data from Sebastian. He has developed a program that selects H2 region from their H alpha emission, and we have taken the spectra for 350 galaxies. I have selected them in order to be sure that the source of ionization is massive star formation. So this implies using diagrams as PPT at the right upper corner of the slide. You use emission lines, and depending on the region in which H2 region lays, we can determine if they are ionized by the massive star formation of an active galactic nuclei. But as well using stellar population synthesis to know if the main component of the stellar population is young or not. By doing the selection, we have selected then more than 8,000 H2 regions in 350 galaxies. This is a lot.
H2 chemistry.
Well, let's talk a bit about metallicity. What I have done is to develop a new method based on photoionization models. These models have been calculated with Cloudy, and the main advantage is that for this likely rich, I have considered 3 different input parameters. One of them, for the first time, is nitrogen to oxygen ratio. The other 2 is metallicity in terms of oxygen abundance, and the ionization parameter. Ionization parameter is briefly the ratio between the number of ionizing photons in a nebula and the number of particles, of electrons, basically. So this covers a large grid of conditions. I have considered the same electron density, ionizing populations with the same age, 1 million years, and I have calculated what's the resulting emission lines that we get from these models. Okay, then, oops.
Steps.
I applied 2 steps to compare the emission line reddening corrected relative to H beta of the most prominent emission lines, including O2, O3, N2, and S2, with the prediction of the models using a chi-square approximation. This code is publicly available in my webpage. I invite you to use it if you need it. The key is that in the first step I get N over O, because the emission line ratios that give us N over O are based on low excitation lines, N2 over O2 and N2 over S2. It does not depend on a ionization parameter. In fact, many authors use these indicators to get oxygen abundances because they do not depend on a ionization parameter, but they are indicators of N over O. Once I have fitted N over O, I recalculate again in a new iteration, constraining the grid to those values compatible with N over O. And in this case, I calculate again oxygen abundance and ionization parameter, using in this case other emission line ratios as R23, O3N2, O2 over O3. Okay, so I get the mean values, chi-square weighted means of these values, N over O, oxygen and ionization parameter under corresponding errors.
Interpolation.
One of the new things I have done for this paper in concrete is that I have introduced a linear interpolation between the models, because in the first version the values trend to concentrate around the nodes of the grid of models. This has not any consequence on the results of our paper. It's just an aesthetic thing. We see some bands but the difference in the bands of these values, this plot represents oxygen and N over O, is lower than the uncertainty of the values that we get. I will show you later other plots in which we won't see anymore this kind of structures, okay? Well, results.
Consistency with 40.
This is for my 2014 paper in which I introduced this code. I have selected a large sample of objects for which we can derive abundances using the direct method. This is the most accurate one. This is in the case that we can get the electron temperature from the spectrum, and then it is no need to use any strong line calibrator. Okay, when I use this line 4663 and I compare the direct metalicities with the metalicities derived with my code, we obtain the plots we see there at the left with oxygen, at the right with N over O, and we see that the consistency is really good. And this is somehow striking because there is in all the others the mantra that models systematically lead to higher abundances in relation with the other method. This is true for many of models recipes that we can find in the literature. But we now know that there are plenty of models consistent with the direct method because we use the same sets of atomic coefficients because the physics is much more elaborated. So perhaps this is the moment to stop, to say this mantra. I don't like your abundances because they are based on models. Okay, let's see if the consistency is good and if the consistency is very good. But there is a trick here. The trick is that I have used the 4363 that gives us information about the temperature. Problem. In the sample of more than 8,000 H2 in Khalifa, only for 16 this line has been measured. So this is not valid. This is the reason why people before used O3 and 2 method. Okay? What do we do then?
Consistency with alpha
Well.
363.
Yes. What we do is to think what happens in the sample of H2 regions that I usually use to calibrate the straw line methods. Well, one of the things that we see in the left panel is that there is a empirical relation between the ionization parameter and metallicity. Of course, this is not for sure that this is going to work for all H2 regions, but it works for the galaxies and the H2 regions that we use to calibrate the methods. So galaxies with lower metallicity have in average higher ionization parameter, and on the contrary, very metal-rich objects have in average very low ionization parameter. By applying these constraints of the grid, we still see a consistency between the models and the direct method. The dispersion is larger, but it is nonsense to pretend that not measuring the 4363 line is going to lead us to a better determination of the abundances that if we are not able to measure this line. Okay, this relation.
Excitation dependence in Khalifa.
Is this a relation between ionization parameter and metallicity valid for our Khalifa H2 regions? Well, at left we see what's the relation between O2 over O3, which is ionization dependent, and O3 and 2, which is somehow metallicity dependent. And we still see perfectly this correlation. This correlation probably has an evolutionary origin. We are not still sure what's the origin of that, but we still see it systematically in all H2 regions that we study. What we see in the right panel is the comparison between an empirical calibration of N3 and 2 and my models, and we see that there is a large dispersion in this case, but we see at the same time with the color code that this dispersion is not owing to excitation. The excitation goes in the same direction that we see in the left panel. Galaxies with low metallicity are in average very excited, and on the contrary, the richer one, the metal-richer one, have in average a lower excitation. Okay, so the origin of the dispersion is not the excitation in this case.
Consistency with our Inogarao.
Okay, the problem arises when we cannot measure the N over O. In my code, this is defined in such a way that we assume what's the relation between N over O and oxygen, exactly in the same way as all strong-line methods do, such as, for instance, O3 and 2. As we see there, I think in the right panel is the comparison. It's a relation between the objects with with electron temperature, my 2014 paper, and my code. In this case, the correlation is still well seen with larger dispersion, but it is still valid. What happens for Khalifa?
N over rho dependence in Khalifa.
In this case, this is at left, the comparison between oxygen and nitrogen for the H2 radius in Khalifa. We see that the relation that we saw before between oxygen and nitrogen, it is not so clear. There is a correlation. Galaxies with larger metallicity have in average larger N over O, but there is as well a large dispersion. So any assumption that we make in this relation probably is going to lead us to an enhancement of the dispersion in the determination of metallicities. And this is what we see in right panel. We see that probably the dispersion that we see between the O3 and 2 parameter and my models, once taking into account the N over O, is owing to a variation of N over O. And this is much more clearly seen in this plot.
HCN without N over rho.
If I delete the previous N over O determination and I assume the classical approximation between N over O and oxygen, the agreement between O3 and 2 and the models is almost perfect. I get the same values. What does this mean? This means that I cannot assume the N over O value to get metallicities. I need to calculate it before. This is very important. This is the main mantra of my talk, in fact.
Radial footings.
Okay, so we have calculated the radial distribution of both oxygen, once corrected for N over O, and N over O for our sample of Khalifa galaxies. We have constrained the calculation for those galaxies with at least 10 H2 radius. So the number of galaxies we have a radial determination is 201. What we see there is the distribution of the slopes of the gradients, both for oxygen and N over O. Contrary to what we obtained before with O3 and 2, we cannot fit a Gaussian distribution in distribution of the slopes, and in fact there are a non-negligible fraction of gradients for which the slope is flat or even inverted. This is as large as 20% for oxygen and is around 5-10% for N over O. And what is more important, the correlation between the slopes of N over O and oxygen is not very good. It's something such as 0.3 or so. There is a certain trend that galaxies with a negative gradient of oxygen present at the same time a negative gradient of nitrogen, but it is not so clear. There are here some examples.
Gradients examples.
Which present probably specific peculiar star formation histories because they can present, well, the most usual situation is the first one with two negative gradients, but there are some cases where we find a flat gradient of oxygen with a negative one of nitrogen, or on the contrary. It's not so simple.
Outskirts.
This is not published in the paper. This is for a conference in Toledo last March. It's a study of what happens in the outskirts of galaxies for radii larger than 2 times the effective radius. And one of the things that we see is that for those galaxies with at least 10 H2 radius at these outskirts, we see a flattening as expected, but this flattening is much more evident for nitrogen than for oxygen. So if we are calculating our oxygen abundances without taking into account that N over O can be different, probably we are taking a mixture of conclusions. It's not so clear what kind of chemical distribution we are obtaining. Okay?
Characteristic of
But
opposites.
I think this is the most important plot of the talk, which is the comparison between oxygen and N over O. It's a density plot for all H2 regions. It could be the blue ones, but the dark points inside show what are the so-called characteristic values, which is the values of oxygen and N over O at the effective radius. And one striking thing is that the correlation is much better, and well, it's the kind of 0.8 or so, the correlation coefficient for the characteristic values, while for single individual H2 regions is only 0.3 or so. This is impressive because this means that even if a galaxy has an inverted gradient of oxygen or nitrogen, just oxygen with a negative gradient of nitrogen, or on the contrary, we can always recover a characteristic value which is representative of the entire galaxy that correlates much better with the other value. This is very important. And this demonstrates as well the importance of getting the distribution, special distribution of abundances, in order to get their characteristic value. This is very important. Okay? Well,
Mass metallicity.
one of the things that for which we can use this characteristics value is to study the mass metallicity relation. This is very known fundamental relation. I have put the famous plot by Cristi Tremonti, 2004, because this is for the first time that for a very large sample of galaxies, this Lodian digital sky survey, this has been shown. We know that galaxies with a lower stellar mass have in average lower metallicity. The effective yield is lower, possibly because they are forming stars more slowly, possibly because most of the metals are, with the potential well of the galaxy, this is not able to retain the metals, so this is why then the metallicity is lower. And I show you as well for the first time a work I'm doing with Salva Duarte, here present, using as well my code to get the relation between N/O and stellar mass. In this case, we still see as well the same correlation, basically because N/O and metallicity correlates. Okay? Well,
Luminosity, metallicity, and Khalifa.
of course, the mass metallicity relation is a sum, let's say, that of the luminosity metallicity relation, originally defined by Legué in 1979 for the first time, because luminosity and mass are well related as well. These plots, what I'm showing is in the upper panels, at left with oxygen, at right with nitrogen, the slopes of the gradients for these 201 galaxies. The most important one are the lower ones, because are the characteristic values. And as shown before with oxygen and nitrogen, there are a very great correlation with luminosity of the galaxy and
Mass metallicity, and
the
Khalifa.
stellar mass. The dispersion is as low as 0.03 dex. This is very little, because the uncertainty in the determination of metallicity is of the order of 0.2 or something. I think it's incredible. Even in the case that you can get the galaxy with a numerical gradient, its metallicity, both oxygen and nitrogen, is going to correlate with a stellar mass very, very, very tightly. Okay? In the case of slopes, as we see, the dispersion is very large. We can find different families of slopes. Statistically, galaxies with lower stellar mass tend to have flatter gradients, but I think this is not statistically significant. The important one are the two lower panels. If we can recover this the relation very tightly, both for oxygen and nitrogen.
Fundamental metallicity relation.
An evolution of the mass metallicity relation is so-called fundamental metallicity one. This appears very few years ago when people realized that there are an additional dependence on star formation rate. When they put metallicity, stellar mass, and star formation rate in a 3D space, it is possible to find a rotation of this space that leads to a relation between the three parameters with a lower dispersion. This happens because for each stellar mass beings, galaxies with a higher star formation rate have, in average, lower metallicity. Is this relation found as well in our sample of galaxies? Well, if we analyze the plots,
Dependence on SFR.
but in this case with the star formation rate has been calculated using mainly H alpha, we see that what we get is that galaxies with higher star formation rate have, in average, higher metallicity, higher nitrogen to oxygen ratio. This could go in the contrary sense than the fundamental relation, but there is a trick here, is that FMR works because it's for each stellar mass being. And in this case, what we show is the relation for all star formation rates. So this is totally normal that happens because there is another fundamental relation.
SFR and Khalifa.
It was this one, sorry.
Main sequence.
No, but the other plot is important. Let me go back.
SFR and Khalifa.
No, the other one.
SFR and Khalifa.
No, it's with the dependence of star formation rate. What?
SFR in Khalifa.
Well, it doesn't matter. Okay. Well.
Main sequence.
Well, the question is that we have a thing which is the main sequence, which writes the stellar mass of the galaxy with this stellar mass. The left plot is taken from a paper we have just submitted, led by Salvador Duarte, studying the masses and the star formation rates for galaxies in the S1 digital sky survey. But in this case, taking the aperture corrections from Khalifa to calculate the integrated star formation rates. And we see that there is a very clear relation between the mass and the star formation rates of these galaxies. And what we see in the right panel is the same relation, but for the 201 galaxies in Khalifa. So it is then normal that we get a star formation rate higher for high metallicity in our sample.
SFR in
But when we analyze the relation between star formation rate and metallicity that we observe, and the one owing to the main sequence, which is the solid, I think, red line, the residuals between these two relations is in the bottom panels, we don't see any difference. There are no trend to find lower metallicity for higher star formation rates. So we don't see any clue of the fundamental metallicity relation in this sample.
previous Khalifa results.
This was already discovered, found by Sebastián Sánchez in a 2013 paper analyzing the metallicities of single H2 regions. He found exactly the same. There is no additional dependence on star formation rate when you analyze the relation between stellar mass and metallicity in Khalifa. Okay, this is very important.
SFR of H2 regions.
On the other hand, the effect of the mass metallicity relation is already seen as well when we analyze the metallicity of single H2 regions as a function. In this case, it's the luminosity of H alpha, which is a proxy of star formation rate. And we see a trend to find that larger H2 regions have, in average, both larger oxygen and nitrogen abundances. But this is, again, a consequence of the mass metallicity relation, because in this sample of galaxies with a larger mass, larger galaxies, have, in average, as well, larger H2 regions. And this is why this is very well seen in the color code. We see this relation.
Mass metallicity in the green peas.
However, the point is that we cannot see the fundamental metallicity relation in Khalifa because there is not any fundamental metallicity relation at all. Or what's the reason? Because we have seen other results in other kinds of galaxies. I would like to cite the green pea galaxies. I have talked a lot about green pea galaxies in the last years in the work I have done with Pepe, with Ricardo Marin when he was here. And these galaxies are very interesting because they present very high specific star formation rates, which is the ratio between the star formation rate and the stellar mass. The luminosity are completely dominated by emission lines. The stellar continuous is very difficult to be seen. When we analyze the mass metallicity relation of these green pea galaxies, and we see at the same time the relation with N over O, we see that they are outliers, in fact, of the mass metallicity relation. One of the plots I showed before illustrates that the dependence on the star formation rate happens for oxygen, but not for N over O. So this links very well with the fact that probably in this kind of galaxies, green peas, extreme emission line galaxies, this has received a lot of pristine metal poor gas that has two important consequences. The first one is that metallicity drops, and the second one is star formation rate boosts. So this is why these present very low metallicities and very high star formation rate. On the contrary, N over O is unaffected. So they cannot appear as outliers in this same relation. So probably the problem is that in Khalifa there are not objects as this, because this is very limited in volume. It's quite representative, the Khalifa sample, in terms of stellar mass, star formation rate, but not in a specific star formation rate. We can see this very clearly when we analyze
Specific star
the
formation.
relation between specific star formation rate. Let me remind you that this is a ratio between the star formation and stellar mass, and the metallicity and N over O. Again, when we take into account the relation between stellar mass and specific star formation rate, in the bottom panel at the residuals, we don't see almost no difference. There is no dependence on a specific star formation rate. So the kind of galaxies that are probably responsible for the fundamental metallicity relation do not exist in the Khalifa sample. What we are obtaining is completely logical. There are no dependent on star formation rate in the mass metallicity in Khalifa sample.
Color in dwarf galaxy.
Well, a couple of results more before finishing. One of them is that color of galaxies have been as well suggested to be used to know what's the age of the stellar population. This is a very interesting result from Lisbon C that demonstrates that there is a correlation between the color of galaxies, integrated colors, and N over O. As I commented before, N over O enhances when it is ejected by low to intermediate star. So when N over O is high, probably the age of the population is large as well, and this implies that the galaxy is red. So this correlation appears as well in dwarf galaxy. The problem.
Color in Khalifa.
We obtain exactly the same results for Khalifa in such a way that galaxies which are redder have, in average, larger metallicities and larger N over O. We don't see just the effect on N over O, we see as well it in metallicity. And we see that then, well, I don't see it is represented there, but there is as well an effect to depend on stellar mass, because the galaxies in Khalifa are redder when they are more massive. We can see this result as well when we compare with the morphological type. This is the Hubble type as a function in the top panels. I'm not commenting a lot about the top panels with slopes, because in general we don't see any statistically significant trend. The most important point are the lower ones. In this case, we see again that galaxies of a late type are in average have lower metallicities, but the dashed line represents as well the average stellar mass for each Hubble type, and we don't see any difference. So this relation between morphological type and metallicity or nitrogen is mostly devoted to the mass metallicity relation. This has been already
mass morphology in Khalifa.
presented in a recent paper of the collaboration led by Rosa. They demonstrate very nicely that there is a bias in the Khalifa sample in such a way that galaxies more massive are redder, and they present earlier Hubble types. There is a very well seen correlation. On the contrary, blue galaxies are low massive, and they have late type. Okay, so what we are seeing basically are always the same correlation that is with stellar mass. Stellar mass is the main driver of the relation with metallicity and nitrogen.
Presence of a bar.
Last result, this is in relation with the presence of a bar. It has been thought for many years that probably the presence of a bar in a galaxy can make the gradient of metallicity be different. And one of the most important results here is coincident with one we published with people of the University of Granada, led by Estrella Florido, in which for Sloan we see that galaxies with a bar have in average larger N over O in the centers than galaxies without a bar. And we see exactly the same result in the Khalifa sample. We don't see much difference in the slopes, but we see that the values in the center are different in N over O than oxygen. What's the cause of this? Well, as I commented before, N over O depends on the star formation history, and probably the presence of a bar makes the star formation history to be different in the center of galaxy, mixed with the fact that probably the gas is driven by the bar towards the center, towards the outskirts. But we see exactly the same result as we obtain. Okay, well.
Conclusion.
So I'm going to stop here just to remind you, firstly, that when the most important thing, two ideas, the main ones. The first one is, I'm conscient that the easiest way to get metallicity is to use the easy parameter, and most of them are based on N2. There are ways to calculate N over O and to take into account that to get more reliable abundances. Please do that. Write me, tell me. I know how to do that. Okay. The second one, very important in Khalifa, is that independently on the shape of the gradient that we obtain in galaxies, and there are many different types of gradients, some of them are inverted, some of them no. The usual way is to get a negative one. It's okay, but there are other combinations. But we can always obtain a characteristic one, we have considered the effective one, that correlates with very low dispersion with the stellar mass. And the other relations that we get for other properties, star formation rate, color, morphology, Hubble type, are dominated by the one with stellar mass. Does this mean that there are no additional dependent star formation rate? We don't know, because probably the effect on the fundamental matter-state ratio depends on other families of galaxies we are not exploring in California. Okay, this is very important. Okay, so that's all. Thank you so much for your attention. More details are in the paper, it's already published, and if you read it, I hope you like it. Thank you.
Thank you very much. Maybe you have some question for Enrique? Come on. No?
It's so clear.
Pepe.
Okay, Enrique, thank you very much. This is a very nice talk. Can you elaborate a bit more on the Greenpeace scenario for the? It's very interesting. The suggesting scenario you suggested for the pristine gas massive inflow.
Yeah.
So how does it would work? What do you think?
How, sorry?
How this scenario
Yeah.
would work?
Difficult to say, but that's for sure that even Khalifa galaxies are receiving pristine gas every time. There's interchange of gas between the intergalactic medium and the galaxies. But the effects on the overall metallicity of the galaxy can only be seen when this fall happens very abruptly. This is the case, for instance, for Greenpeace, because when we compare the masses of the galaxies with the masses of the high velocity clouds or whatever, they are on the same order. Probably Khalifa galaxies are receiving gas very slowly because of the fall of the gas in the halo of the galaxy, and this implies that this does not affect the relation between the metallicity and the mass. Probably there are regions of these galaxies or in the outer skirts of interacting galaxies in which we can see this effect. But when we study statistically for all galaxies, we cannot see that. On the contrary, this family of galaxies are more representative in the always low and deep gas sky survey. Greenpeace are just an example. Probably this is happening in all very different scales, because Greenpeace, we know that they are around 1,000 in a sample of galaxies which is around 1 million. So these are not enough wave to make the fundamental velocities to appear. But it is something more subtle in the sense that probably it's happening in many, many different galaxies, but not in the California ones.
So maybe in the other parts, maybe it's a good idea to, in the other parts of the Khalifa galaxy, maybe this effect is taking place on this. No? This is what you suggested. The inflow of pristine gas is more important in the other parts of Khalifa galaxy.
Probably making analysis of the azimuthal distribution of metals, we can discover such a kind of things.
Thank you.
More question? I have one question. I'm looking to the one of your first slide.
Mm-hmm.
I found myself some cases with nitrogen over oxygen around -2.5.
Yeah.
Also, these low values are due to some special.
Well, the lower limit for nitrogen in the models are
or
-2.
related to the population 3 or something like that.
Well, these are probably fake points. You know, when you have a sufficiently large sample of objects, you have to look to the medians or average, not just single cases. I don't know. It maybe depends on the measurement of the emission lines. It is for sure that one should not expect such very low nitrogen values if two regions is metal rich. But if you force the models, probably you can get such a combination of values. But this does not imply that this is real. The main point of the paper is to take the average not to try to.
I have seen these low values in the galaxies studied by Cambridge people about the Dample-Lyman alpha system and all this at redshift 3. And I don't know if this is this have something to do with the difference in the local population and in population at higher redshift.
Yeah.
Because I remember what I have been discussing long ago with Max Pedini, that he said that of course these data were really well measured and they are not with big error.
Yeah.
And they are measuring always this very low nitrogen over oxygen abundances. And of course they have data with very low metallicities. And I don't know if I don't know how is the situation now.
I honestly
That's why I
have several doubts about the results of that paper, because it is quite strange to find such low nitrogen values combined with very high metallicities. I would like to see the spectrum. But it is true that there are several models, perhaps you can get them. For instance, in the positive feedback model. In positive feedback model, the gas is recycled very quickly. So metallicity tends to grow very quickly, but N over O does not, because the low intermediate stars haven't had enough time to eject the nitrogen. But this is an extreme model. I don't know if it's the case for high redshift galaxies.
Because I was curious, following your talk with the data of Khalifa, we always have nitrogen over oxygen over minus 1.5, let me say.
But this is for very few galaxies.
And no lower than that.
No.
So that is...
no, but minus 1.5 is very low for the metricity of the
galaxy
of
Khalifa. That is so...
we are now trying...
Dwarf galaxies normally is 1.5.
Yes. We are trying now to make some chemical evolution models with methyl that helps us to explain such a kind of combination of values. But we are taking every time the values of entire galaxies, not just single H2 regions, because probably these are spurious points in our diagrams.
I have also another curiosity. Sorry, this is, well, maybe it's a stupid question, but why normally in galaxies we saturate the metallicity at some point? I mean, in the center. If you move to the center, you get 8.8, 8.9, and no more than this.
Because probably we are run out of gas. There are not any more gas to form new stars. And when we receive new gas, this gas is metal poor from the
because, I mean, the people who are working with quasars, they claim sometimes metallicity over solar, 2 times, 3 times over solar. But in normal galaxies, we saturate. I remember a work we made made with Isabel, and then this work was also repeated by Pepe and Piligi, and we always saturate at some point metallicity.
Yeah, but I would like to know if the method they use to get the metallicity in quasar is the same that we use, because for instance, depending on the models, for instance, Christy Tremonti gets twice the solar value for star-forming galaxies in the slow end, because their models are not well calibrated. So are we sure that we are using the same methodology? I think that the most important point is try to be consistent every time, regardless of we are using direct method or models or what kind of models. So it is strange indeed that we get such a large metallicities even in quasars.
Well, I don't believe very much, but
you know what I mean?
but I mean, I do believe your metallicities, but I always think that we are saturated at some point, and we cannot get any galaxy with metallicity. 9.3 or something like that.
Probably less than that. Yeah.
Okay, Isabel?
Hi, Enrique. Very nice talk.
Thank you.
It's just a small question concerning barred galaxies. You said, if I well understood, that N over O is great, it's bigger for barred galaxies. That's a result of that paper by Florida, right?
Yes.
Has
Let
it
me
been-
think. No, it's lower for barred galaxies, I think. Yeah,
In any case, it's different for barred galaxies and for non-barred galaxies.
in the center.
Is there any dependence with mass taken into account already?
No. No.
So you don't know whether the difference is because of mass?
The mass of the galaxy, you mean?
Yeah.
I don't know if they have studied this parameter, but I don't think so. It depends mostly just on the presence of the bar. The problem is that the sample is very limited because they put constraints about what kind of galaxy it was possible to get the metallicity.
Yes,
So I don't know if they were able to study them depending on the stellar mass being.
Mhm.
Mm. It could be a good point to study, yeah.
Okay, if there is no more question, thank you again.
Thank you.
Muy bien.
¿Mucho bien de tiempo?
¿Qué?
¿De tiempo está bien?
Ah, está perfecto.
Bien.